When we're talking about AI in really high-stakes situations, think self-driving cars or even medical diagnoses, a single wrong answer can be a disaster. We absolutely have to be able to trust its predictions. So in this explainer, we're going to dig into a huge challenge with AI confidence and a surprisingly simple fix that's making AI both smarter and a whole lot safer.
Okay, so let me just ask you a question to kick things off. Imagine an AI gives you its single best guess, its most confident prediction for something really, really important. Would you be willing to bet everything on it? Like, for instance, what if it was for
A medical diagnosis? In a field like this, one wrong prediction can be incredibly dangerous. Sure, the AI might be right 99% of the time, but what about that last 1%? How do you know that the prediction you're looking at right now isn't that one mistake? That uncertainty, that's the huge problem researchers are trying to solve.
So to tackle this, a whole new way of thinking is taking hold. Instead of giving one single high-stakes guess, it offers something more like a safety net for the AI's predictions.
This idea is called conformal prediction, and the core concept is actually pretty straightforward. Instead of giving just one answer, the AI gives you a small set of possible answers. But here's the magic part. It comes with a guarantee. It can promise you that, say, 90% of the time, the actual correct answer is going to be somewhere in that set.
So think about it this way. A single prediction kind of leaves you flying blind. If it's wrong, you have no idea. But a prediction set, that gives you a known margin of safety. It's the difference between an AI saying, the diagnosis is definitely X, versus it saying, hey, I'm 90% sure the diagnosis is either X, Y, or Z. That is a massive leap forward for building trust in these systems. But, and there's always a but, right? There's a catch. This safety net has a pretty serious flaw. Sometimes it's just way, way too big to actually be useful. Okay, so here's why that happens. When an AI model makes a prediction, it spits out a whole list of probabilities for all the possible answers. And usually, you get one or two really high-confidence guesses, and then this long tail of a bunch of other options with teeny-tiny, almost meaningless probabilities. The problem is, some of the current methods, like one called adaptive prediction sets, or APS, they grab all these low-probability guesses when they're building the safety net.
And this is the heart of the problem, and the researchers themselves put it perfectly. Because of this long tail, the algorithm just keeps adding tons of really unlikely answers into its safety net, just to be safe.
So what's the point of a safety net if it's the size of a football field? It's like asking a detective who the main suspect is, and they just hand you a phone book. A list of 50 possible medical diagnoses isn't that much more helpful than a single wrong one.
But this is where the researchers had this incredible aha moment. They started to question the very thing that everyone just assumed was important, the probability numbers themselves. They asked a really wild, counterintuitive question. We have all these super precise probability values, right? Like 0.001% or 0.002%. But what if? What if all that detail is actually just noise? What if we only focused on the ranking? Which answer is number 1, which is number 2, and so on, and just threw the rest of the numbers away?
And the results of that little experiment? I mean, look at this. They are absolutely staggering. Check out the inception model. When it was using all the detailed probability values, the average prediction set had over 88 answers in it. 88! But by just using the ranking, it dropped to just over 6. For the VIT model, it went from more than 10 down to 1.6. It turns out those little probability values weren't just useless, they were actually making the problem worse. So this incredible insight led them to build a brand new, much smarter way to create these safety nets.
They call it Sorted Adaptive Prediction Sets, or SAPS for short. And the idea behind it is just so elegant. It mostly relies on the simple ranking of the answers, but it keeps one, and only one, probability value, the confidence score of the model's number 1 top guess.
Okay, so here's how it works. SAS starts with that simple, solid ranking. Then it just glances at the confidence score of that single top guess. If the confidence is really high, SAS knows, okay, this is an easy problem, so it can make a smaller, tighter set. If the confidence is low, it knows it's a hard problem, so it should make the set a little bigger. And all those other tiny, unreliable probabilities in the long tail, it just swaps them all out for a single constant value, basically telling all that noise to just go away.
All right, so the big question, does this simpler approach actually work? Well, let me tell you, the results really do speak for themselves.
On the ImageNet benchmark, the data is just crystal clear. The old method, APS, gave you sets with an average size of almost 21. A newer method, RAPS, got it down to about 3.3, which is pretty good. But SAPS, by just ignoring all that probability noise, gets the average size down to just under 3. It is, by far, the most efficient method we've seen yet. To put that into perspective, SAPS was creating prediction sets that were, on average, more than 7 times smaller than the old standard method. That is a gigantic leap in how useful these things are.
But look, making the set smaller is only half the story. Is the system actually smart enough to know when to be cautious and when it can be really confident?
And the answer is a huge yes. For an easy image where the AI is super confident, SAPS produces a really tight set, maybe 3 or 4 possibilities. But for a hard, really ambiguous image, it automatically expands the set to around 9 possibilities, giving itself a wider, safer margin for error. It actually adapts to how hard the problem is. It's brilliant.
So, at the end of the day, all of this research really boils down to this one powerful takeaway from the paper. In this big quest to make AI trustworthy, we always assume that more data, more detail is better. But in this case, all that extra precision from the probability values, it was just redundant noise.
It just goes to show that sometimes the most elegant and powerful solution is actually the simplest one. And it leaves us with a really fascinating question. If ignoring all this complexity led to such a huge breakthrough in AI confidence, where else might our AIs be overthinking things, getting tangled up in details that just don't matter?